So, Shaun, you were here just a minute ago, so that microphone is, you may want to hold it. That mic stand doesn't work very well either, so.
Hello? Is that going to work? Let me play with this a second. Okay, so my name's Shaun Phillips, and I'm also working with the Space Launch System flight software at Marshall Space Flight Center. I'm the project lead at this time, and as Deanna mentioned, it's an in-house development, and we're very proud of that we had that opportunity to develop that software in-house at Marshall. And of course, as the lead, I'm responsible for all the phases of software development, though I'm focusing on testing in this discussion. But development, of course, covers the whole life cycle, from requirements through design and verification. And so like Deanna's here, she's now a former member of my team. And there's several other people in the room that have supported SLS over the last several years. My topic here is the discussion of switching from manual versus automated analysis and verification. And it's a little different than what Deanna's talking, because I'm talking the integrated build after delivery informal test. This transition is actually in progress. We did not start with tools. That's been a big lesson learned, even at this level of testing. It's a time-intensive, highly inefficient process we've been following. We have been able to get through our first formal qualification testing, though, but it's taken a lot of incremental activity, a lot of time, and it's actually our largest team is our test and verification team on the project. As Deanna mentioned, we're in maintenance now, and as we start looking at Artemis 2 and beyond, we realize that we have to get automated to posture ourselves to be able to more quickly deliver changes, even for Artemis 1. If we don't get there, the testing is what's going to slow us down. So, as an overview, I'm going to talk a little bit more about flight software context and the vehicle. Deanna covered a lot of that, but I have a couple of different slides. I'm going to talk about our current development and verification strategy, a little bit about how our manual verification process works, and then what we're going to do to automate our process. And I have a few words on some forward planning. So where is the avionics that the flight software actually runs on? It's actually in the core stage avionics. The flight computers are up here in the upper ring. This is the vehicle blown out. So of course you guys know about Orion. There's the adapters, launch vehicle stage adapter. But there's also avionics in the booster and on the engines and up and down the core with things like the MPS and the thrust vector controls and RGA, RENUs. All those pieces of avionics exist all through the vehicle. So just an overview of the different kinds of software we have. As I mentioned, the flight software resides on the flight computers, and we actually have 3 flight computers. They're in a voting architecture. And we refer to that, often you'll hear one of us talking about our FCOG, that's our Flight Computer Operational Group. But other software includes the ICPS, and the vendor ULA is providing that software. The RENU, which is our nav unit, comes loaded with software that's critical to our nav positioning, and we use data from that in our GNC calculations. Also the RGA, the rate gyro assembly, comes from Honeywell, and it provides our rate data to the flight computers. And then the engine controllers are heritage. They've updated the software quite a bit, but there are 25 engines with updated software. Whoops. Come on. So, just to let you know, we actually are developing 2 CSCIs. We're developing what we call, and we weren't very original with naming, the Flight Computer Application Software, CSCI, which provides all our pre-flight, pre-operational activities and all the flight critical and non-critical software functions necessary for on-pad, pre-launch operations, processing, integration, all that activity, the launch countdown where we go autonomous, as Tia mentioned, on Monday, and then engine ignition, and then ascent of the vehicle through a couple modes of flight. The grid run application software is very similar. It's actually built on the same code base, but instead of running the GNC software, it executes a predefined thrust vector control, actuator position profile, and a predefined engine controller throttle position profile. So it can be executed in a hot fire on the B2 test stand at Stennis. And that will be a test of the core stage that you will see hopefully later next spring before it's shipped from Stennis to the Cape for integration into the SLS vehicle. So as Deanna mentioned, we have several development standards. We have to follow 7150.2, and as she mentioned, we're on B. And I noticed out there that the NASA table has several copies of C, but I still have my B copy because that's what we're following for Artemis 1. We haven't committed to a time frame yet for upgrading to C. Thinking to be with Artemis 2, but we haven't committed yet. That levies requirements on us because we're Class A safety critical, and we have to show that compliance. And we do a lot of that through our software development plan, has a tailoring matrix, and we point to all the different artifacts that support our compliance. And then also, critical as being Class A is we have to meet the CMMI maturity model for development version 1.3, and we were assessed at level 3 for all process areas earlier this year, at least the third time, maybe more. I can't remember how many times we've done it now. I believe we're stepping up to version 2.0 for the next round. I think that's required. Okay, similar to Deanna, I also wanted to just touch on our Agile Development. As she mentioned, we do requirements development outside of the actual development sprints, but we also do, and my focus is more on the test side. So there's a lot of testing done within the development group itself as it builds up the changes. But the actual verification and sign-off is done against the SRS, is done by the test team. And so they are independent. They're not the developers. They're allowed to talk to the developers, but they are independent from the development team and have to have a lot of knowledge about how the system operates to understand how to set up tests. So this is a chart we share at every one of our test readiness reviews to show the buildup of testing. As Deanna covered quite thoroughly, there's unit testing, both code coverage and functional unit testing and MCDC coverage testing done down in the design team, and this integration testing. All this is we have clocked over 15,000 hours of testing in these venues at this point, and we continue to run nightly, as Deanna mentioned, and that's a critical foundation for all of our verification activities. At this transition point is when CM builds the dev tag, and there is some, it's not any verification, but they do a confirmation flyout and verify at least that it works the way we thought it would, that the build is the same build that the development team gets. And that's been important because we do want it independently built by the CM team, and we need to make sure it's the same build. Then we enter into the design, T&V team's venue, and I'm going to talk a little bit about what a DLR is versus this testing. But this comprises our T&V activity, and this is the requirements verification in our test lines. Just like the design lines, we run in a simulation environment with Maestro and Artemis, and we have the FCOG EDUs. We have 3 EDUs in both of these lines, and everything else is simulated in the verification labs for flight software. And as you notice, the fidelity of the venues increases. So down here, we're doing, sometimes this functional unit testing is done on the individual developers' workstations, and it gets built up even in here to the triplex level. But as we go to this venue, it's just the triplex. And as you know, the cost and schedule starts going up. So these tests, you can run all of our unit testing overnight, and it takes about 12 hours now to run all of it. This testing, which I'll talk about now, a nominal run where you do an entire flyout takes at least 15 minutes. And there's some extended tests just to verify other capabilities we have to do that take hours to execute. After that, we deliver to the SIL. You saw that if you saw the tour, and they do integration testing there. It's comprehensive, what's called DVO verification. That's where all the stakeholders have levied their requirements against the system, and all of them, including us, participate in a review of the data that's generated in that lab and provide feedback and review. We've just completed phase 1 of that. And there has been feedback that has led to some changes, and we actually have a maintenance release going through this cycle right now because of results in phase 1 verification testing. Some hardware-driven, as Deanna mentioned, where hardware doesn't work quite like we thought it did. And in some cases, we missed a couple things. After the SIL, there's also a sister lab called the CITIF that if you saw the tour or the picture Tia put up the other day, that's a stage representation, similar hardware, where we'll be doing a green run, similar environment. We'll be doing validation testing with the GRASS CSCI here very, very shortly with the stage controller, which is the ground control for the green run test. After that, it gets integrated on the vehicle. It's going to be used for green run, like I mentioned, and then it will be used initially for ITCO, which is some early testing when they start integrating the vehicle. It's also then, of course, be used for EM1. So the first flight is our ultimate validation activity. Wanted to also give kudos here to IVNV. Their S3 environment that was mentioned in their earlier talk has been very useful in finding some unique problems that we couldn't have identified with our testing environments here. They're able to, because they simulate the hardware, they can actually emulate process type failures that we cannot do on the real hardware. And it's been very interesting results. So, as I promised, little definition of how we set up our requirements. We have 2 levels of requirements. We have Blackbox. Those are the ones that exist at the FCOG level. You get it's the response to an external stimulus at the system level. So if you get a power on command to one of those avionics boxes, what is the flight computer going to do? It can be much more involved, but that's a simple version of a black box requirement. At a design level requirement, and we call those DLRs, the behavior and stimulus is only internal to the system. So those are module level. What does the propulsion system do specifically when it sees that power on command, maybe to a propulsion system box, and it may not be, and it's not visible outside of the CSCI. So our test team tests both types of requirements, and verification of both of these, of the entire set of about 1,000 requirements, is required to complete our verification activity, and we own one DVO that's for the verification of all these requirements. I'm not going to talk DLRs in this talk anymore much, because the DLRs, we follow a similar test philosophy as the unit testing. That's required. You can't look under the box if you're running the system as a whole. You're looking at data that's coming either out of the simulation environment or down on telemetry. So here's just a little representation of the differences. So here the black box is communicating with the simulation environment on the real buses, so they're all running a copy of flight software. They're all sharing data, and Artemis controls the inputs to all those boxes. The DLR testing, it's on a single board computer, and the harness executes the module. And we provide test vectors, and like the design team, these test vectors were written by the test team, and they execute the module at that low level. So both of these have documentation. Because we are this Class A, we have to produce a test plan. In the test plan, we trace our requirements to test procedures. Test procedures are actually captured in doors and in Subversion, where they're actually controlled. And then we have to produce a test report with all the results, pass-fail for every single requirement. So going on to why we want to change what we've been doing. This is our process flow for verification. So we develop the test plan. We start developing test procedures. This is a manual process right here, and you guys probably can't read it, but it's the logical steps when you're generating a test procedure to operate the lab and create the data for each test case, and I'll talk a little bit more about how we break those down. You go and you develop what it takes, and so I didn't really mention it, but of course, to do those stimulus, a lot of our requirements are off nominal, so you have to inject a fault. So you have to write fault injection scripts, and you have to build all that. Then you dry run, and then you do a manual data analysis, and you repeat this iteratively until the results are either pass as you expect it because you finally got the test right, or the test is right, but it fails. And you iterate on that process. This is always manual in our current process. And just as an example, currently a full flyout is about 12 gigabytes of data. So it takes some work. So we do all that build up, we get all the procedures written. Every single one of them is reviewed by multiple stakeholders outside of the flight software environment, which is another reason it's not in a sprint. We've tightened up on their allowed time, but it still takes longer than it should. So eventually we build up that whole suite. We have a TRR, and we go into formal test execution. So we do batch up, even in this mode, we do batch our runs. So often overnight we'll run 20 to 40 test cases. Even at 15 minutes apiece, that's about the limit of what you can really do. But you don't know if they passed or failed till you go, again, do that manual process. If you're lucky, some of the smaller nominal cases take 3-4 hours. But a lot of them take multiple days, especially the more complex ones requiring multiple permutations. So we've been working with this paradigm for years. We've known it's not ideal. We've known we couldn't support it. And while there is some analysis tools, and there's a few we've used here, we didn't have anything that we called accredited or formally verified that we were willing to stand on to say, yes, this is good enough to support a Class A verification activity. So, whoops, sorry, went too fast. So this basically repeats what I just said, just in some words, just emphasizing that it's manual. You got to pull the data. You got to manipulate the data. You actually pull it into an Excel spreadsheet, and you have to manipulate the data. And then you have to evaluate it against the pass-fail criteria you documented in your test procedure. So just a high-level, very, very high-level overview of how this process evolves. Sorry, giving away the punchline. I'm not good at this. So this is similar to that example earlier, very, very simple. At some kind of time, the FCAS shall send a command to some kind of box. So that's a very, very simplistic one. A lot of ours are, like I said, off-nominal. There will be multiple off-nominal scenarios that could trigger a certain kind of abort or caution, and there'll be fairly complex requirements that require multiple test cases to verify. This one's pretty simple. You'd look at the bus data, you check the time for that time you're looking for. You check it that at that time that command was in the data packet to the box, and you'd create that test package for the community review. You know, this would be the pass-fail step, you know, that the command was found in that data packet right where you thought it would be. So that one, pretty simple, but, you know, repeat it 500 times. And like I said, this is a simple one. There's many test cases, many requirements that require multiple permutations to fully test. So there is multiple test cases. I don't know what the average is, but it is over 1. We have several that have 64 or more test cases because of the complex nature of the software. So you'd see it in the plan, the trace, identify the methodology, and by the way, test is our preferred methodology as Class A software. You can inspect, and we do have a handful of inspections, and I don't think we have any demonstrates. Our goal, like I said, primarily is test. And then in the test report, you'd see the pass-fail results. So here's our proposed automated process. You're still going to have to develop all those test cases because you got to develop the pass-fail criteria. You need to know what you're trying to do, and you have to develop how you're going to do it. But instead of doing that manual analysis every time, we're going to develop a module that's going to work in a tool to confirm that pass-fail status. And it's going to pull, and you're going to generate all the associated artifacts. You're going to have to develop the fault injection scenarios and all those still. But then when you do the dry runs, this automated tool will extract the data and evaluate the data against the module logic, and then it'll be able to tell you, hey, it passed or it failed right then. At the conclusion of those set of batch runs overnight, the test engineer is going to be able to come in and say, hey, they all passed. Hopefully, if you're after TRR, they all passed because that's our goal, and be able to put that right into our STR. And so that's our goal, and we actually are well on our way to meeting that goal. We have an automated tool that has been in work for several months. It is an in-house developed by the tools team. We have a tools team. Class C safety critical tool is going to be certified, and we actually had the TRR yesterday. So they're in the process of testing it right now. It has 2 modes. I keep hitting that. Uh-oh. I'll keep talking, but I need the charts back. Can I do that myself? Okay. Has 2 modes. It has a command line interface mode and a interactive mode. The command line interface mode is what I'm going to focus on here for a second, but the interactive mode is going to let you do on-the-fly data analysis. The command line mode is going to let you build these modules, and they're going to be available. You can write them. They have to be written, their code, in either Python. Right now, we're going to upgrade it to support C++ also in the next iteration. And these modules will be executed from the run data. So the service will pull in the run data as soon as the run's complete. It develops a database based on the measurement list that you pick. So there's measurement data. You have to tell it what data to pull out of this data set. And then it will run the module and report that pass-fail output for every one of these. So that's our goal. And like I said, we've been building that up. The tools team had their TRR yesterday afternoon and got approval to go forward into testing. Hopefully that will be complete verification by early January, because we actually have a use for it coming up soon. So this is my last slide, well, second to last slide, but so a summary and a forward plan. So we really felt that automated testing was where we needed to go to reduce human interaction. Every time you do that manual analysis, you have a potential for human error in reviewing the results. And by being repeatable and automated, it's going to allow for easier regression testing. It's definitely going to improve our test data evaluation time frames. It right now takes weeks to get the analysis complete and build that test report. And it's going to improve our overall schedule efficiency and turnaround time, because once this is deployed, we're going to start building modules to support all the testing. So hopefully, sooner rather than later, we'll be able to pull a whole regression test and just execute it with these Sherlock modules. So our forward planning is to complete the certification of the command line interface. That's actually what we're testing first. Like I said, our goal is early January. We have a pilot lined up. We have configuration data that supports all the different launch windows that are going to be available, and we have to confirm all that data. And that was one of the reasons we realized we have to have this sooner, like now, to be able to do those data confirmations without taking months. That piloting effort is supposed to happen at the end of January. That's why we gave them the goal of being done by mid-January. And then, as I mentioned, that forward plan to start building a suite of modules to support regression testing. There's even some long-term planning not mentioned here. Maybe try to integrate machine learning to even help with some of this data analysis going forward in the future. That's a little bit further out, but it's on the radar, and I forgot to include that as a bullet on the slides. So just a reminder again, my name's Shaun Phillips. There's my contact info, and if you have any questions, feel free to email me or call me at the number on the charts.
Great. Thank you, Shaun. Any questions?
Thank you. It was very interesting to hear the detail. Gosh, I don't know what to do with this. But I was curious to know, you've talked about the SLS, V&V and the automation and testing. Is there a system of systems level test to integrate across the ground system, SLS, and
The SIL
Orion?
supports this. The SIL actually has emulators for the ground and for Orion, and so they do integration testing, cross-program integration testing. Not only there, but in each of the programs has their own labs where their software runs for real, and then we send emulators to them. I don't believe there's any system plan until the vehicle's put together where all three systems are actually running their own software in their native environments, though, at the same time.
Other questions? Nope. All right. Thank you.
Thank you.